Okay, 11.3 is the integral test, and I'm going to put and in quotes, estimates of sums, because what it means is estimates of sums using the integral test. So 11.3 is all about how to essentially do the reverse of Riemann sums. So we should just call this reverse Riemann sums chapter. Okay, so what we have is, for example, 1 over n squared. We're summing that up. We can't start that one at 0, so let's start it at 1. And so let's just for the moment not have any curves here. Let me see. I guess this is a PDF, so I have to erase them. There you go. Just kind of erase these for a second. Okay. So I'm looking at these bars, and I'm thinking that this is 1, and this is 1/4, and the next one is 1/9, and so on and so forth. So what do they add up to? Well, I'm going to go to this blank page for a second, and just let's talk about that a little bit. So I have this box, and I have another box, and I have another box, and another box, something like that. Okay? So this is 1. This is not drawn to scale. 1/4, a 9th, a 25th. So what does that have to do with an integral? Well, if I make all these have width 1, I can then superimpose this other scale underneath. So for example, I'm going to let, right here, I'm going to let x equal 1, and right here x equals 2, and here x equals 3, then x equals 4, x equals 5. Okay, I just realized I made a 25 when I should have made a 16. Whoops. Okay. And so if I want to look at the function f of x equals 1 over x squared, then right here I'm going to have a height of 1. Right here I'm going to have a height of 1/4, height of a 9th, height of a 16th, and so on and so forth. So the curve that goes through these points will look like that. And if I were to integrate from 1 to infinity of this guy, this will under-approximate the actual sum. N is equal to 1 to infinity. Okay? Hopefully that's not too hard to read. I'll change the color. Here we go. All right. This is an under approximation. But let's say instead we do this a little differently. There we go. Let's not do that. Let's forget we said any of this. Maybe we want to overestimate. So now what do? Well, why don't we take this scale and shift it over. Okay, well, 3 is kind of cocky. There we go. Now what does it look like? Well, now it's totally different. So now this little point is up here. This little point is gone. This little point is up here. This little point is up here. And this little point is here. There we go. Now we want to estimate f of x is equal to 1 over x. Now we're going to be over approximating. And you may say, well, wait a minute, we use that same integral when we were under approximating. That's true, but we're going to use it differently. So because this goes off to infinity, and this little area is infinite, all right? So this area, we don't want to deal with it. So this is a kind of a hack. Okay, we're gonna use this rectangle, but then we're gonna use the integral for the rest of the approximation. Over here, we're gonna use the integral. So we want to over approximate is going to be 1, that's the first rectangle, and then you're going to integrate from 1 to infinity 1 over x squared. I meant to say x squared, you knew that. Okay, dx, right? And you may say ho, but this guy is an under approximation. That's right. So the actual is in between these guys. Okay, so the under approximation looks like this, and the over approximation is actually just one more than the under approximation. So we know that the actual value, this value here, right, is right in there. There we go. And that's really all there is to that. I mean, if you understood that, you're good to go. And if not, you might want to watch this clip a couple more times. But let's just look at a couple things. Okay, so does this guy converge? Well, we know if we compare it to 1 over n, these terms are bigger. And if we add up the 1 over n's, we know that that's bad. So if this is bigger than something that's bad, then there's no way it converges. No way. But we can also use the integral test, and so you guys can try this. You can integrate from 1 to infinity, natural log. You may use x, and I don't care if you, so if you use x or t, you're implying that it's a continuous variable. When you use n, you're usually implying that it's not, but I don't care. You can use x's wherever you want, or n's wherever you want. But this is just saying this guy, so if this guy gives answer, then yes. But we already know the answer is no, so we expect this thing to fail. Okay, do you want me to show you? Okay. Just do it over here. Okay, so if I go natural log of x over x 1 to infinity or something like that, some kind of u substitution. What is it? Okay, so yeah, it's u substitution. So this is the kind of trick you're going to use. So you're going to say, you know, u equals natural log of x, derivative of natural log of x is 1 over x, and then you're going to do u substitution. Natural log of infinity is still infinity, but the natural log of 1 is 0, so this lower limit changes. And then you integrate this thing, you get u squared over 2. And so you're going to get